this course here, and we'll show you the pro forma in the next class there. So exactly which are the chapters will be considered that will be discussed in depth. And then after that, we'll move on there. So this is the CO, and this CO course outcome will be linked to. So one thing, by the way, that the this course outcome will be linked with the questions asked by the evaluators, because there is the criteria that the question cannot be set outside the course outcome, because it has to satisfy the course outcome there. And then those course outcome are linked with the program outcome there. So this link is, if you can read the Malay there, if you can read, so this there. So you see there, this is linked with these program outcomes. So similarly, we move on to the next section there. Which one is this? I think it's the 17. So that's okay. Now we go to the next one. So for our general discussion, that is the HVAC and building energy management. What is the basics of it? That's being discussed in this chapter. So if you consider here that if you introduce this, then in the introductory section, we can say that if this is the building here, you can see the cursor. The space need to be air conditioned, then that space is linked with quite a few number of equipment there, and discharge is also managed to follow some of the rules there. So in this case, if we start from the beginning there, then we say that ventilation here, means the fresh air is coming through this, and this one is the damper there. So how much ventilation air will go through this? It will be electronically controlled by the damper, and then after that, so after that is coming to this point, then there we have the filters there. So the filter is dependent on how much precision filtering is needed in this room there. So as we said earlier, that the hospital will be one way there, one criteria have to be maintained there. So if we go to office building, then another criteria have to be maintained there. So all these things will be considered in this case. So we move on further there. Then we have the supply fan there. So as the fan is discharging to the room there, so this is a forced draft fan. And when this flow is discharged from the room to the environment, then this is induced to draft fan. So in this case, the forced draft fan is, or the supply fan is shown there in the loop. And then after that, we need to control the humidification, cooling and dehumidification there, because around 60% this humidity have to be maintained in the room so that you can get the comfortable air conditioning. Otherwise, too much dry, you get the that is throat dry there, and then you get this problem, human uneasy. So that is why the humidity have to be maintained, and the desired temperature, how much temperature we have to maintain there, that is to be maintained at that point. But the point is that once the heating, dehumidification and cooling is done there, then after that, if the variation of temperature is there, then it is being taken care of, and humidity is their variation that is being taken care of by this heating and humidification, because it has got that is the PLC control system, and then how much the excess air, how much the temperature of this the air will be raised there, passing through the surface of heat exchanger, and then the dehumidification. If it is too much dry there, then have to be done there humidification there. Accordingly, the amount of water will be sprayed to maintain the humidity there. So after that, once we come to this section, that is the place where this thing will be done. Means the room, the criteria of the room will be maintained here. According to ASHRAE, they say that it's 26.4 degrees is the standard temperature. But here we find that most of the rooms they're maintained a little bit below that. So that is the choice of the people, and according to that, it is to be maintained. Now the question is coming that how much load will be considered there. There is a criteria that this will be the thumb rule. The load will be this. So all the load will be added there: equipment load, door opening load, because when the door will be open, then hot air will come from outside, and if it is cold country, then other way around. And then the person living here, he will discharge some heat there, and then he will also contaminate the air there, making the carbon dioxide, and then the moisture and internal heating. All these parameters have to be considered for calculating the room load ratio line there. So when the room load is calculated, then this the flow and the temperature and the heating and dehumidification and heating and humidification, they will be linked with it. And then accordingly, the room temperature, how much flow will be there to maintain the room temperature that is being, and how much temperature drop down will be there, it can be considered. So here one thing we want to realize that the total load is the sensible heat and latent heat. So latent heat of vaporization is coming from the moisture that is being vaporized there. If you consider the psychrometric chart, then we'll see it there, as well as we go to the sensible heat there. So how much temperature rise there? So all these, the total load will be calculated here, and then this equipment will be adjusted accordingly. So after that, when it is coming to the induced draft fan, so the discharge of it will come through the damper there, and then how much will be exhausted, that is exhausted air will be considered how much from the total, that will be dependent on what is the comfortable air conditioning will be maintained in this room area. And then some percentage will be because if 100% rented off, then if it is not the requirement, then the consumption of power will be more there. So that's why, to minimize it, following the standard, people not be yes, uneasy, people not feel uneasy, as well as the air conditioning purpose will be such. Accordingly, the percentage will be mixed with the ventilation unit, and then it will follow the loop. So this is more or less the schematic of a typical air distribution system. So if we see there that the small building and the smaller space and the larger space, if we go for this air conditioning there, then as the fixed costs are there, that is the fans, blowers, and then dampers, and then dehumidification and humidification unit, heating and cooling unit, all these stuffs are there. So it is not economic to cool a space which is too small there. That is, and is also not very economic to if it is too large a space there. So that is why from this table or distribution of floor space and energy used in commercial building sector, we're talking about the buildings. And so in commercial building, we can see that if the floor area is less than this, 10,000, then this research is being done, considered 73 buildings there. 70, that is number of buildings being considered 73%. Then the total area, this much percent is being considered there, and floor space is 20%, where this the investigation is being done. Then we can see that the energy use is 20 there. So this many buildings being considered in the region, their commercial building, one space, and then these are the floor space of them needed to do the air conditioning. Then we find that it is around 20% of the energy use. So if you go further up there, 10,000 to 100,000, then we find that the number of buildings, there are 25 of the total number of buildings considered in this research, and floor space is 45%. Then we can see that 38 is the energy use. See, the energy use increases, but if you go further up there, the energy use further go up over there. So what we linked there, that if we increase the greater than this percent, then the energy use is 42%. So if we remain within this, then is around 38. So there is a scope of doing optimization. So that is the information we want to transmit. So move on further there, that building system design and interactions. If you see the building systems, how this management is done, this building heating and ventilation, air conditioning system, how it is maintained there. So if you see these, the schematic diagram, then we can see that the architect is coming with, they are contributing there with the contractors, and then they're making the building. So following the design of the civil engineer and the load and this stuff being controlled, being considered by the civil engineers. But the architecture will find out the aesthetic beauty of the building there. So he can also discuss with the civil engineer to find out that what area will be for what specific purpose there, and how much temperature will be maintained where.
kitchen temperature will be maintained at a lower, and then go to there. Office section will be one building is lots of things there, and then it can be high-rise building, can be also the shopping mall can be there. So if so many things there, then lots of variations of the
variations of the requirement will be. So with this, the information going, design and building information is going to make this building there. So this is, once the design is done there, at the same time, then heating, ventilation, and air conditioning system of the building will be taken care of. So this heating, ventilation, and air conditioning system is directly linked with the control system of it. How sophisticated the control system will be maintained there, that is linked with it. And this control system is the heating, ventilation, and air conditioning control engineer will design it. So once it is, there is a big industry, these consultants and companies, they are doing these things. So with it, once it is, the information is coming there, then now another point is involved with it, which the maintenance and load calculation and what will be the size of these, that is done by the HVAC mechanical engineer, plus the refrigeration unit will be how much. So all these phenomena, all these things will be considered by the mechanical engineer. So there, he will do the selection of the equipment, HVAC equipment manufacturer. They will talk with the manufacturer. So many of you are experienced in industry, so that you know how they when they want to buy some equipment, they are either pump or fan or whatever it is, they go for tender and then communicate with the manufacturer. So when the bid, participate in the bid, then further explanation will be could be done there, as well as the negotiations done there. Because it's reduce the price, they say no, cannot be, then this criteria will be what are the basic specifications that have to be maintained there. Some sort of adjustment can also be done in the last moment. So with realizing all these things, so we can see that the building system design interactions, this way they are interactive with each other. And then this is not the one party will do it. It looks that it's a joint effort to successfully get all these things done. So then we move on further up there, then HVAC system design process. So if we see the design process, then we can see that the design, heating, and cooling loads of it. So we got to get the information about the how much cooling will be done. That is guided by the comfort and air quality criteria. Previously, we discussed about it, and we said that there are 5 criteria maintained in the comfort air conditioning. They are comfort criteria. Those we will, in course of time, we will see all these things. And according to region, it's also very severe. And these are all physical data, because the people get the feelings and then they say that now feeling comfortable. So that is the load being considered. Yet. And then people dress, and then of the people, all these things are contributing equally in it. So that is why the comfort and air quality criteria is directly governing this design, heating, and cooling load there. Next, coming the weather data there. This is also a very vital issue there. If the weather data variation there, refrigeration data changes, and then we need to do either increase refrigeration or decrease this. And not only the weather data, as well as the climate data, also consider that seasonal change there have to be. Then we go further there, that the building design, which spaces there is the big room there, how much the hall room will be there in
or in a flat, what will be the drawing room size, this and that. All these things are coming from the building design there. So from this, once they get this information, design, heating, and cooling load, it's moving on further over there. This is the component sizing and selection. So this is the very crucial stage there, because once the equipment is purchased, it cannot be changed. So that these all these criteria have to be considered in component sizing and selection there. So once it is selected, then this selection will be guided by the system selection there. That is where it will be, what size will be there, and then what will be the, then next coming the control systems will be there. So in this system selection there, whether it will be refrigeration, first need to do the refrigeration, otherwise the air condition cannot do it. So for the refrigeration, we have to use the either absorption refrigeration system or vapor compression refrigeration system. And we find that when you will study the refrigeration, then we'll see that if the 100 ton, more than 100 ton, then this absorption refrigeration system is preferred there. And then if we go to below 100 ton, below, then it may not be the this economic. So that definitely everywhere the economy is the vital issue there. So realizing that the selection of the system selection will be chosen. Then go to the controls there, what type of control will be there, how much precision will be there, and then all this is guiding the component sizing and selection criteria there. Depth size can be reduced, size can be increased by control system. Then get into the estimate of initial costs and estimate of operating costs there. Initial cost is coming out with the establishment cost there. That is individual equipment cost there. And then when go to the operating cost, how much fuel needed there, and then what are the salaries of the operators, the clerical staffs there. We go to the high officials there, they coming in the estimation of initial cost there. Say director, MD, all these people there, they involved. So with this, we move on further there, the life cycle costs. Because the life cycle costs is involved with the how long the equipment will last, warranty period of it, and then these the system will without any alteration how much it can. Then gradually the capacity or efficiency will drop down. So need to do the balancing and modernization. So other balancing and modernization that will be the last step over there when we need to we need to maintain the capacity of the system, heating, ventilation, air conditioning system. So these points are needed to consider there. So we go on further there, then HVAC system operation. So we can see that the HVAC system, if we see the operation of it, the building is there. And then the facility of the management, building management, they will guide the control of the building there. It's a huge plant type of thing there, because the one building is high-rise building is just like as a plant. It has lots of components. There are lots of considerations have to be taken. So in this case, the facility management unit have to be there. They will maintain the facilities of the building. Starting from the fire hydrant, sprinkler, to end up with the heating, air conditioning, ventilation system. All these things have to be considered for the facility management team there. So they will guide the control system of the buildings. Then HVAC system is linked with the control system. Then the utility company, they are coming. Utility is HVAC, all these things, they are utility. That company will feedback there. Then finally, the feedback is coming from the HVAC equipment services company there. So they will tell us that how frequently they can, if the system breakdown is there, how frequently they can repair it, or the system can be continuous operation can be maintained. So all this stuff is linked with the HVAC system operations. So with it, we move on further down there. Then we can see that the typical NRC prices. So this is the changing with the changing of the fuel, that is the NRC prices is changed to that. And then that will also tax on the or that guides the HVAC system cost analysis there. So realizing that in mind, if the equipment is run by the electricity there, then we can do this, electricity and diesel generator, or oil and diesel fuel by diesel generator, and then can use the natural gas and then run the engine there, and then can be used for running equipment. That can also be concerned about big equipment there. So it can then also be that way. And then if this is used for the electricity generation there, then that is also playing their role, that how much it will cost. Then coal-fired furnace can be, or coal-fired generation, electricity or power generation can be used there. Gasoline-fired can be used there. Oil or diesel fuel can be used there. The electricity, we consider that when we generate the electricity, then these things are considered there. So in this case, we typical energy prices, we see that the generation of electricity, energy content, and unit price, and energy price per unit price, how much this energy is cost. So when diesel or diesel fuel is being used there, so if we see the electricity BTU per kilowatt, there, then equivalent oil or diesel will be equivalent this many BTU per gallon. So this many BTU per gallon, if it is, then this number of BTU, how many, from there we can calculate how many gallon, equivalent gallon is needed there for running the equal amount of energy there. So then we find the unit price is there 0.10 to 25 per kilowatt hour if it is done there, electricity directly used there, because the price is estimated from the national grid, how much we get in. So realizing that in mind, if it is oil and diesel fuel is used there for running the equipment, then we get $2 to $4 per gallon there. So you see there, the hydroelectric and these things, it reduces that. So then is per gallon, we get 2 to 4 there. So we get here per kilowatt hour is $0.10. Here we get 0.05. Gradually, the price is going down with the quality of the fuel there. So in this case, we see the natural gas, then heating value, we get 10 to the power 5 BTU per ton there, the unit. So from there, we get that unit price is this much per ton there. So this is the bigger unit than this stuff. So from there, we get that the per unit kilowatt hour is price reducing there. So the economic will be to go for the lower price of it. So similarly, gasoline, and after that, the coal is the lowest there. But there are other criteria are playing the role there. So if we use the coal there, then it's a pollution prone. More it will pollute the environment. So we have to have other equipment, and the coal discharging to the environment, coal particles discharging to the environment have to be arrested within the DOE level of requirement there. So realizing all this mind, it is all these things, it's find that there are merits and demerits, both of it. This every fuel they have their own merit and demerit, but there is a compromise that is to be done for the economic operation of the fuel used for the running of the HVAC system. So now we go to further down over there, then we see that the conversion factor and constants are there. So what we see there, that in many occasions we will need to convert the units from BTU, British Thermal Unit, to SI unit and these things, because not all the problems given in the SI unit, because the ASHRAI, they do it in BTU, British Thermal Unit. So we have to solve the problem in BTU, British Thermal Unit. So in that case, we have to have our easy understanding. The conversion table should be with us, and the exam hall will give us the thermal, conversion factor, conversion table, psychrometric chart, all these things. So I don't think there will be any problem yet. So with it, we move on further there. As this chapter. Then after that, we will go to very basics of some discussion before going to refrigeration and the refrigeration circuit. Before that, we will study 2 more chapters there. So what do we find there? Then system analysis techniques. So what we have seen earlier, that the outdoor air is coming and is getting the recirculated air from this the exhaust fan there, and or the induced draft fan there. Then induced draft is sucking the air from the occupied zone and then discharging it to the environment. So with it, we come to the some percentage, as we say, is discharged to the outdoor air, and then from there is coming to the supply fan, and from there is coming to the occupied zone here, and the heat and moisture is being considered in the occupied zone, and accordingly the load is calculated. So if we consider the heat and moisture, there is considered as LZ. So what can be the thermodynamic relation will be represented by the term LZ. So it can represent the M into GH, that is mass of the fluid into change in enthalpy X. So that will give us the amount of energy needed to, or amount of energy considered for this case. So we go on further over there, and then air conditioning performance. If you study the air conditioning performance, then you can see that the cooling capacity BTU per hour, and also simply supply air temperature. So if the increasing condenser temperature, so you see there that increasing condenser temperature, if it is going down there, then cooling capacity BTU increases there. So that we find from this graph. And similarly for the powered. So if the powered, if we go to supply air temperature increases, then cooling powered also increases there. So with this graphical information, we find these two, the cooling capacity decreases with the increasing condenser temperature, and because that is the need to maintain these the lower level of temperature there, and when this condenser temperature going up, then have to maintain the upper level of temperature there, so the power consumption increase. Now we come to the empirical curve fit there. If it is done, then the load can be calculated by, this is a series. With this series, the load can be calculated where Ts is representing the surface temperature, Tc representing the condenser temperature there. And then go to the work done is also can be represented by these series there. So with it, we move on to further down there. We can see that the power and pressure characteristics for a fan, their power will be W if we consider, and delta P PSI is the pressure loss there in the system. Then power increases to be the flow rate. That we also see the Moody chart. Moody chart, we can see the similar thing there. And then here also is with the increasing in flow rate, pressure-wise also decreases. So with this, we move on further there, and then we can see that the WF, where is representing this C meter cube, that is the capacity of it, the fan in meter cube. So with it, we move on the power consumption W and air flow rate. If it is, then fan gradually increases with the flow rate, fan power, and air conditioning power is the decreases with the dropping down of the temperature there. So then where should be the optimization point? There's a scope to getting the optimum total the power consumption, so that we can find the total power is there, then have to consider this is the operating range there. So we move on further there. Then yes,
Dr. Kazi, sorry.
yes.
Can I is it possible for you to maybe like highlight the part that you're talking about, because it's quite hard to follow.
Cannot see the cursor. This is
sometimes it's not moving.
This is
not maybe moving. Maybe sometimes maybe if you can like use a pen to maybe circle so that we can see better.
Oh, okay.
Thank you.
So in that case, we do. This is actually PowerPoint, eh? So then in that case, we have to go for this one. Eh? Then we can do. Where is? Is, let us see. So if we go this slideshow, then there is a pointer should come here, but I don't see the pointer here. Why not? I don't really understand. Is it PDF or PowerPoint?
I think it's on the bottom left.
Bottom line? Yeah.
Bottom left. when you click present PowerPoint just now, I think I can see like a paintbrush image in the bottom left.
This one, huh? Yeah.
Yeah, maybe that's it. I'm not sure.
Yeah. You are correct. Yeah. This one. Okay. Yeah. Can be. So now you see the refrigeration system performance. If we consider the refrigeration system performance, then the evaporator temperature. See there that the evaporator temperature is maintained on depending on the cooling load there and how much temperature what to drop there. It's in this case, our case is the room where that is we want to maintain the evaporator temperature. There, consider the evaporator because you consider the vapor compression refrigeration system, then our evaporator is our cooling space. So we can see from this that when we go for this, the evaporator temperature gradually increases there, then refrigeration capacity is gradually increases the refrigeration capacity because the evaporator temperature is higher there, so more cooling is needed to maintain the temperature. And these evaporator temperature go further away there, then further increasing. This is that simple information we can get from here, and lot of the performance capacity tone, and it depends on the temperature there. So it increases with the increasing of the temperature in the space where we want to do the air conditioning. Then we go on further there that ninth order fit to capacity is a function of evaporator temperature. So we get some sort of table card also can be used for fitting this card there, and then the capacity can be evaluated from these empirical equations there. So we go further there, then refrigeration system performance tables, linear regression. If you do it, then select independent and dependent variable from form of regression. So we can see the capacity there is, these are the equations being developed by the people from the original data, and then they developed the equations which can be used to calculate the capacity. So we go on further there, you see the engineering equation solver, it's a software, and then using the engineering equation solver, the capacity can be calculated. How many tones, considering the evaporative temperature is a function of the capacity there. So we see here that as well as when it is increasing there, gradually increasing the temperature, then it's getting the capacity curve downwards. So we did information. We come to the optimization using engineering equation solver, schematic of an HVAC system with power input. So there are other these softwares for calculating the heating load, and this engineering equation solver is one of it. So with this schematic of an HVAC system with power input, we can see that the compressor powered this air conditioning. So compressor power increases when you need to do more throttling there. So that is the one of the criteria which needed to realize it. So if we see here the loop once again, that compressor power consumption is this, and air conditioning here, and then the refrigerant is moving through the compressor there and then coming to the direct expansion coil there. And then after the direct expansion coil is going to the air conditioning section there. So you see if you remember this, I think all of you remember it, the vapor compression refrigeration system there. So after the compressor, discharge is coming to the condenser section, and then after the condenser is going to the throttling valve before it's coming to the section where it wants to cool it, supply air where you want to cool it there. So in this case, we can see here that the compressor power is WC flowing through the air conditioning unit there, and the refrigerant want to maintain certain temperature there, TF, and then this one is going to maintain this supply air to zone TS. Then this is the mass flow rate of this through this forced draft fan is moving towards it there. So all these things can be used for calculating the compression work there by using these equations and these empirical equations there. Similarly, WF can also be calculated, and total can be calculated, WC plus WF. That is the air conditioning compressor and other units there, fan and other units there. So fan and other units, other auxiliary units altogether is the total load there can be calculated. So with this optimization using engineering equation solver, then we can see the power with the flow rate. So then we see that the fan power increases and air conditioning power decreases. With it, we can, if you consider the total, then we can get this concern about this. The total can optimization we get from the bottom line of it. So we get to this there, the optimization again on power kilowatt and air flow rate. Now you see there, there's many diagrams as this Ashrai, they use this FPS system. So they use the pound mass per hour there. So air flow rate and the power consumption is the fan power increases with the air flow rate there, and air conditioning power is decreases with it. So the minimum is, that is the point what we maintain in our design there. So we go on further there, schematic of a vapor compression refrigeration system. There is another chapter only on the vapor compression refrigeration system. And then there will be another section will be on the absorption refrigeration system. What are the different materials we'll be using there, and what is the difference between this and similar like our the refrigeration course we offered here. That is, I think, is the undergraduate level. The refrigeration course is offered there here in this University of Malaya. So there detailed discussion being done, but as we are recollecting it, so we will study some of it this stage, so that when we will move on with it in our calculations and this and selection of the equipment and then calculating the load there, then it will be helpful. So that is why we're doing it. If it is that, then start with the compression there. So see the compression inlet is there, and from the evaporator discharge, it is coming there. There should be no paper, and there should be no moisture content in it. Compression. If it is two-phase flow, the compressor cannot compress it, and then there will be vibration as well as the there will be surging, and then the compressor will experience the damage of it. So that is why these when they design it has to consider in such a way that the compressor inlet will be such way it's the amount of heat absorbing the evaporator. We'll start from here, so here the amount of heat will be absorbed in the evaporator so that the refrigerant will be 100% paper will be here. And then after that, it's compressed and then coming to this point to there, and then it's cooled in the condenser there. So when it's cooled, then this heat is dissipated to the cooling liquid. Then after that is the expansion valve there, so that the throttling effect is. In expansion valve, if we consider, then we can see that after the expansion valve, the enthalpy will be constant there. So in compression, we get the entropy constant. Rather, in expansion valve, we get the enthalpy constant. So that need to keep in mind. And then after that is coming to this. So is the throttling effect is there in this valve. So when the throttling effect there means it will condense some of it, and then refrigeration effect will be there. That means it will condense and then drop down below the evaporator temperature. Then it's coming at the inlet of the evaporator after this, and then this evaporator, it absorbs QE. That amount of heat is going there. So after that, the cycle will continue. There, which one is what is actually we don't need it, because we already know it, that this W represents power, and then zone load. There we say that this is the sensible heat plus latent heat is giving out the total load there. So we did. So now we move on to, what's the time? It's 14:26. So maybe after 1 hour, I will give you 5 to 10 minutes break. So maybe another 3-4 minutes we will give you. And then the books, or the referred books, will be HVAC, heating, ventilation, air conditioning books. All the reference will be given in the next class there. So here we go to this one. Oh no, yes. This lecture slides 3. Now, so this one, this chapter we will study. We will just very fast. We will move through this one, which will to recollect our previous knowledge there, so that it will be needed for our calculations. That is why we going through this. Is that okay? Huh? Then after that, we will go to the, then after that, we'll go to the refrigeration heat pump. After that, we'll go to so Jeremy, Brian, Muhammad, no Shakir. We go to next chapter. So this one we are recollecting from our some knowledge from fluid mechanics and this stuff. Yeah. Sorry. Oh, by the way, I need to discuss with you about what is your preferred mode of lectures. Do you prefer the online or prefer physical lecture? Which you prefer, physical or online? Uh, uh, Jeremy, Yok, Nuradi, Brian, which this mode of lecture you preferred? Because we have to inform the management. What do you prefer? Is online or physical?
So I think online is okay for me.
Online, okay. Huh?
Yeah.
Okay. There is another point, so I can just tell them online is preferred by them. Online. Yeah, this is number one. And number two is this in this course, 50% coursework and 50% is final exam. Is it? Because
Yes.
yeah, so final exam is 50% and coursework is 50%. So so in this case, coursework normally we do it like this: one class test. If you agree, all of you agree, then we'll go like this: one class test, 20 marks. Then one group assignment, group maybe 4 to 5 of you could be in one group. So the group assignment will be a little bit bigger assignment there. So a group involvement is needed that will enhance our capability of collaborative, cooperative learning, as well as that will develop our skill of teamwork, and these things are involved there. So that is why if we prefer the group assignment 20 marks there and class test 20 marks, then 40 gone there. The third one can be individual assignment, so that it will monitor whether you that is you are updated with the class or not. If some assignment is given in the class and if the evaluator asks you to do this assignment and submit online, because we all online going on. So submit individual assignment, individual assignment, maybe altogether individual assignment will be maybe 5. Then 10 marks there. So that will cover 50 marks. And in the final exams, these 3 questions there will, because 3 CO you marked it there, 3 CO, so there will be 3 questions there, and each question they will have 2 parts there. One is theoretical part and another is evaluation, that is problem solving. So in that case, 16 into 2 and 1 is 17, something like this. Is it all right? Huh? 17 into 1 there, or 17 or 18, maybe one. Huh? One problem will be 18 and another 2. This, or 2 will be 17, or somehow it will be 50, will be managed there. So this is about the evaluation and this sort of things. But anyway, I'll discuss with Dr. Mashul and then we'll finalize it, what he prefers there. But at this moment, this is roughly about, if you agree, then I can tell him that you want the one class test, one group assignment, and 5 individual assignments. Is that okay with acceptable to all of you?
Since the individual assignment, there will be 5. Is it not possible for the individual assignment to be of a higher percentage than the group assignment?
Yeah, individual can be percentage higher. So in that case, it will be much load on individual person. So you like it, then it can be 15 can be the individual, and this the 10 can be accordingly. Highly percentage means 20 you want individual assignment, and group assignment you want 10. Is it?
Yeah, I would like that. I mean, for
Okay.
me personally, but I'm not sure about the rest of the class.
Yeah. So okay, the way you want there, because normally we don't reduce any mark in the unless they don't say some part of the report missing and this. Unless it is like this, then we don't reduce any mark there. So if it is the group assignment, then load can be distributed there. But anyway, is your choice. So 20 for individual assignment, 20 for class test, and 10 for group assignment. Okay, is that all right with all of you? Is it okay? So what about others? Jeremy, is it okay? Ryan, is it okay? No, Shakib, is it okay? Ahmad Harit?
Sir.
Okay. Because once we settle, then we'll be consent to being recorded. Yeah, that's the thing. So whatever the thing you say that it will be recorded, so we cannot change it, because we'll follow it, because we'll set the accordingly. And then the individual assignment, if it is more marks there, then it will be a bit complex there. Is that okay? Agreed? So is all right? Jeremy, is all right?
Yeah, it's okay.
Okay.
Yeah.
So this one I will give Dr. Mashul this information. Now we come to this. It's now 45. So I give you 5 to 10 minutes a break, and then after that we'll again start discussion. Is that okay? Because this break, we
That's
must
okay.
give you the break. It is as per EAC requirement. EAC, they say that continuously cannot talk too long there. So that's why I give you 5 to 10 minutes of break now. Then we'll continue this chapter and then see that how much we can go for today. And then the next The rest of the things will be continued in the coming classes. Is that okay? So I give you a break now.
Okay.
Okay. Mm. So it's, that is this. Mm. This PDF, I think, it's the point. This PDF. Should we start now? Jeremy, should we start now? Yok, should we start?
Yes.
Now? Okay. Okay. Now you see, this chapter is containing some information about fluid mechanics and heat transfer there here, and followed the book of this fluid mechanics fundamentals and applications, Sinjel and John and Kimball there. So if you see there that the wind turbines, they are the funds they are using the available wind energy for extraction, transformation of the energy from one form to the another, or one form to another usable form. Usable form. You can see the pointed. So these are the flowing of the wind and then passing through the wind turbine and then transfer the wind and the velocity energy, wind velocity energy to this electrical form of the electrical energy through the wind turbine there. So here this the Bernoulli's equation is also useful in the preliminary design stage there. So transformation of the one energy to the another form, and to the application of the energy equation and concept of energy equation, Bernoulli's equation of these things. We long time ago did these things there. So just be recollected so that can be we can remember it and we can use in evaluation or calculation. So now the objective here, we need to apply the conservation of mass equation to balance the incoming and outgoing flow rate in a flow system there. We consider any flow system as a control volume there involved. So the amount of energy coming in and going out of the system have to be equal if no change of the internal energy or system energy is changed. And then go to the understand, we will, or understand, you already know this, but the recollect the Bernoulli's equation and apply for solving variety of fluid flow problems there, and to work with the energy equation expressed in terms of heat use. So there's the that is hydraulic energy there, level, hydraulic energy level, and the total energy level there means the kinetic energy level and the hydraulic energy level together. So all this information we need to have here for our future use, and work with the energy equation expressed in terms of head and use to determine the turbine power output, pump power requirement of this simple previous knowledge there, because here we need to know it, because we have to calculate the minor losses, major losses in the pipes and the flow equipment there, and then calculate the total energy losses, so that the fan capacity have to be how much pressure head have to consider by the fan, as well as what will be the capacity of the fan will be used in there. So all these things are here to consider in this chapter. So what we find here that from our previous knowledge, we know that the conservation laws of energy, conservation laws of mass here. So if we do and then the conservation of momentum there, so momentum equation, energy equation, continuity equation, all this stuff we need to remember there. So we move on further there, and this the conservation of mass, if we consider from our knowledge, if we consider a system or a control volume there, then mass in minus mass out is equal to change of system energy in the system mass in the control volume, dmCV by dt. Rate of change will be represented by the, if no change there, then is M in is equal to M out there. And the rate of change of the mass content in the control volume, and that is that depends on the system performance there. So this is the ideal case. But in reality, actual case, we find that there are major losses, there are lots of losses there, which transform one energy to another energy, form of energy. So that is one of the points we need to consider there. And the linear momentum equation and Newton's second law, we find that if we considered the rate of change of momentum in the linear, then mp1 minus mp2, that is indicating with the effect of the flow velocity is being considered there. And the second, according to this, second law, we can find that the rate of change of the momentum of the body is equal to the net force acting on the body there. And conservation of momentum principle, consider the momentum of a system remains constant when the net force acting on it is zero there, and thus the momentum of such system is conserved there. And then we move on further there, the linear momentum equation, and in this case that we say that if the linear momentum equation, we consider that is moving on a straight line, the fluid moving, and there's no vertical component of this is being considered. So Newton's second law is easily referred to as the linear momentum equation. So we move on further there, that conservation of energy, we say that E in minus ED in the control volume, the energy in minus energy out from the control volume is equal to dECV by dt, the rate of change of the energy in the control volume will be equal to the difference between the E in minus T out there. So with it, we go on further there. If we consider the conservation of mass there, then we can say that this simple example, we can say that 1 mole of the hydrogen
if it reacts with 1 mole of carbon dioxide, that it produces 1 mole of oxygen, that it produces 1 mole of water. Yeah. So if you consider these in terms of the mole, in terms of the kg mole there, then 2 kg and 16 kg giving us 18. So it reflects the conservation of mass there. So if we consider the conservation of energy, then mass transfer to energy there by using E is equal to mc squared, then we can also, as this is irreversible equations there, but it can be considered how much energy can be produced, where C indicating the velocity of light. So now mass and momentum flow, mass and the momentum flow there is, if we consider the linear flow of energy in the curved surface there, then if you consider that the delta mass is flowing on the differential mass flow rate, could be represented by area into velocity into density there. So mass flow rate can be represented by rho Vn dAc, and the total, that is the differential amount there. So if you consider the total, then it can be integrated. Then we can find it out, the AC2 minus AC1 over there, and can be represented by R2 squared minus R1 squared. Similarly, the path function have inexact differentials there. Consider the path functions. So then we can find that 1 to 2 there, delta m is equal to this, integrate the whole region there, then we get m total, and this m total is not equal to m2 minus m1. Rather, it's the integral of the differential mass altogether in that region. So we move on further there. Then, if we consider the flow stream in a pi flow there, then we can see that this turbulent flow is being bounded here, is represented here, there, and then the average is represented. V average is the integration of the V average is the integration of the area, cross-sectional area, into Vn into dAc there. So then it is giving us the average flow velocity there. And then if we want to calculate the mass flow, then it will be on the surface of the area. Total mass flow is a differential mass, and integrating on the surface, which is virtually equal to rho into Vn into dA there. So with this understanding, if we move on further there, then if we consider the average velocity Vn, then if the average velocity remaining on the surface, consider the one velocity there, then which will be equal to the volumetric flow rate will be V into S rate, and mass flow rate will be the volumetric flow rate into density there, or volumetric flow rate divided by the specific volume that is giving us that data. So we move on further there, conservation of mass principle. If we go further there, then we can see that the total mass entering the control volume during the time difference delta t minus the total mass leaving the control volume due to this in that delta t time, which is equal to the net change of mass without the control volume during delta t. And it can be represented just at the bottom line over there, that m in minus m out is equal to delta m CV. So then this is equal to del m CV by dt there, and is, as an example, if you consider that the amount of water coming inside, if it is 50 kg and draining out is 20, then and 30 kg, then remaining is 20, which is represented dmCV by dt there.
So with this understanding, we move on further there that total mass within the control volume is representing mCV is integration of CV rho dV there. So rate of change of mass within the control volume is equal to d dt of rho dV there, integration of, and normal capacity of component of the velocity. If we consider this is the velocity along this direction, and we consider that the flow area will be perpendicular to the direction of flow. So in this case, if we consider the normal there, then v dot into cos theta will representing the v component in the n direction. So with it, we can write out rho v cos theta Vn instead of Vn there along this direction. Mass flow is perpendicular to the flow direction. Then we can find out rho v into n vector into d. So net mass flow rate will be integration of the control surface delta n, which is representing rho v and dA, and it can be rho v into n into dA there. So with this understanding, we move on further over there that the general conservation of mass equation can be written down that d dt is equal to rho dv is the linear component of it plus the this component which is the perpendicular to the flow direction there. So the total will be 0 because the coming in is a rho v dv and going out is a rho v and into dv. So with it, we can similarly here, if we consider this surface area there, then the component here is considered the horizontal or this direction. Then we can say that Vn perpendicular to this component can be considered v cos theta along this direction, and that is equal to area A there. So in that case, area cos theta will divided by cos theta will give us the inclined area there at that place. So in this case, we can write down the mass flow rate to rho into v cos theta into A by cos theta, which is virtually rho v there. So with this, we can say that the total the general energy conservation of this mass flow rate, it can be written that d dt cv into rho dv plus a summation of rho v and A there minus the in this amount, out this amount, and in this amount. So this virtually can be represented by rho, a summation of rho v in and rho v out. Area remaining the same there because you transfer the implied area to A by this time. And then it can be represented by, finally, it can be represented by this change in the control volume as this mass flow rate, change of mass flow rate in the control volume will be equal to in and out, the difference between these two. So if we use this Boas equation there, that dB divided by dt, which is representing d dt rho b dv plus rho b v dot n dot there. So if we consider the b equal to 1 and b equal to m there, then it can be a represented dm system by dt, which is equal to this. So with this, we move on to further there that this is not only be valid for the boundary, fixed boundary layer, rather it can also be valid for the moving boundary layer there. So if you move, consider as an example, if you consider the seed layer and then the pressing it, so the boundary layer moving gradually inside, discharging while discharging the fluid direct. So for that moving boundary layer, it also valid this conservation, and it can be represented by VR is the V minus the VCS, where VCS is the local velocity of the control surface. And at that point, relative to a fixed point, if you consider this local velocity is relative to a specific point on the surface, or on a specific point on a surface in the control volume there. So now we go to the mass balance for steady flow process there. Then we can write down that the total mass will be equal to 2 plus 3, that is the 5 kg in case the control volume there in is equal to E out there. So where we have M1 is equal to M2, and according to our knowledge, we can say volumetric flow rate into density is giving us this mass flow rate there. And that mass balance for the steady flow process is giving us the conservation mass. So special case incompressible flow, if we consider the incompressible flow there, then we can find the boundary. The Bernoulli's equation is valid for the incompressible flow there. So for the incompressible flow, we can say that E in is equal to E out meter cube per second. So we can say V1 is equal to V2, and we can write down V1A1 is equal to V2A2. This is steady incompressible flow, single stream equation there. So with it, we move on further there, then solve a problem there. Mind you, the assignment will not be like this. Assignment will be a bit complex there. So read this problem, but we reading it, solving this problem, which is recollecting our previous knowledge. So in this case, we consider that a garden hose attached with a nozzle is used. So when the area reduces, then the velocity increases. When the velocity remaining constant, or when the flow rate remaining constant. So if the data, you read it quickly, the data given there, need to calculate the volume and mass flow rate of water through the hose, and the average velocity of water at the nozzle exit. So you read it, huh? So in this case, the volumetric flow rate will be total volume flow rate 40 liter divided by how many seconds it flowed. They said it 50 seconds there, so we get to this many liter there. So mass is equal to, we get the rho into V there. So we know if you consider this, the density is 1000 kg per meter cube, that is 1000 kg per 1000 liter, is coming 1 kg per liter. So with it, mass flow can be calculated there. So go to further there, the cross-sectional area of the nozzle and the hose pipe, they are different there. So if we know the cross-sectional area of the hose, 2 cm there, so pi d squared by 4, from there we can calculate how much will be the velocity through the hose. And through the nozzle, if the area reduces, then the velocity will be increased from our understanding. So AE is the pi RE squared, and from there through the hose, it is coming the cross-sectional area. Hose cross-sectional area is 0.52. This is stuff that is about 4 there, and then from it we can write down VE is the V by AC there, and 800 liter, but this is coming 15.9 meter per second. So if the area reduces there, then velocity through this will, through the, you see the nozzle is the hose 2 cm and reduces to 8 cm at the nozzle exit. So this 0.4, this is the hose, and the nozzle is do pi d square by 4, then is coming this much. So it's coming 15.9 meter per second for the nozzle exit, whereas the hose it will for the hose, as is the bigger diameter, so it's coming 2.5 meter per second there. So from this understanding, we can see that the velocity we need to pump power will be needed, not pump, that is the area, because our refrigeration unit, we use the pump, and then we use also chiller there. Pump, chiller, compressor, all these things for our refrigeration unit down there in the case of HVAC system, where this distribution system and the duct system are for the air distribution in the buildings there. So realizing that in mind, we can see that when the duct reduces the dimension, then the duct loss increases there, and velocity also increases. Cannot have the velocity unlimited, because I have to control the velocity at which it has to be discharged in the heating, ventilation, and air conditioning system there. If too much velocity, then they will feel, the people will feel uncomfortable there. So that is why the discharge velocity and the recollection velocity, that is through the distributor and through the receiver. Through the receiver, that discharged the air is coming through the receiver or the collector. Is going back through the induced draft fan, and then going, because induced draft fan is creating a negative pressure there, so that the flow is coming from this system through it. So we go further there, and now you see the mechanical energy and the efficiency there. So what is the mechanical energy of a system? Flowing fluid. If you consider flowing fluid, then mechanical energy will be equal to flow energy, that is remaining as the pressure divided by P by rho there, plus the kinetic energy, half mv square. If m is 1 there, then half v square, plus potential energy Cz there. So we get the flow energy plus kinetic energy plus potential energy. This is total mechanical energy of a flowing fluid per unit mass. So this is the standard equation. Then if we consider the mechanical energy change of a stream flow, or in a this horizontal flow passage there, the change in mechanical energy, if we consider the point 1 and point 2, 2 points being considered, then we can write down here this P2 minus P1 by rho plus V2 square minus V1 square by 2 plus ZZ, the Z2 minus Z1. Where is the cursor? What's the pointer? So in this case, I have a look to here. Yeah, this the mechanical energy, change of mechanical energy
as 2 points. The next equation, delta E mechanical P2 minus P1 by rho plus V2 squared minus V1
squared by 2 there. So it's coming Z into Z2 minus Z1 there, because the difference between 2 points, the similar type of energy have to be subtracted from the similar form energy there. Potential energy has to be subtracted from potential, kinetic energy from kinetic, and pressure energy or mechanical energy, flow energy from there. So then with what we can find from here, that if this delta E mechanical, if it is more than 0 there, then what is the utility? What is indicates that this change represents the mechanical work supplied to the fluid there. Because if it is a pump, that means you adding energy there in the pump. Because through the volute, if it is moving there, then its enthalpy increases there. Though it is asentropic, but the energy is increased there. So in this case, it's added there. But if it is flowing through the turbine there, then it's the delta E mechanical from the system is less than 0, because it is losing energy there. So it will show less than 0 there, negative. So in this case, this is indicating that the total system energy dropping down due to turbine, because you're extracting energy from there. So with this understanding, we move on further there, that the head, this pressure head there, that is the pressure head there, and delta, if we say that the total amount of mechanical energy, pressure energy, so in this case, M into P2 minus P3 divided by rho there. So this is basically, this is the head minus this head when it is flowing through the turbine. This is the water turbine, and is operated by the, this is the water turbine and is operating the generator there. So once it's operating the generator, then electricity produces there. So in this case, we can find that how much mechanical energy, the pressure energy will be there. So M into difference in pressure divided by rho. So P2 minus P1 by rho there, which is equal to mass into delta P by rho. And the kinetic energy will be here, the no flow velocity there, because this head just maintained there. And then here also same, so that the change of kinetic energy, V2 is equal to this kinetic energy is equal to at the point 2 and 3 there. V2 is equal to V3 and Z2 is equal to Z3 there. So if it is, Z3 is equal to Z2, and then V2 is equal to V3. So those terms will be cancelled out. So remaining the energy output M into delta P by rho there. So similarly here, we can find W max is equal to M into delta T mechanical, which is equal to Vz into Z1 minus Z2. So in this case, mgz, which is equal to h rho g there. That means h into rho into g there. And then this is equal to, that is the pressure energy, which is indicating for unit. So in this case, if the mass flow is m there, m into gh, which is indicating how much energy will be extracted from the turbine due to this head difference there. So with this understanding, we move on further there, that if we consider this surface A, which is equal to per unit is G into H there, and then from this B, discharge from there, if you consider it, then rho into G into H there. So that is the amount of energy. So PE is equal to 0, there are no head, and then we have the extracted energy by the turbine here is giving rho into G into H. So with this understanding, if the people say us that evaluate the neta mechanical, that is turbine mechanical this energy, how much will be there? So it can be calculated by mechanical energy output divided by mechanical energy input there. So E mechanical output by E mechanical input, that can also be written like this, because it can mechanical output minus the losses, which will equal to mechanical output. Is it mechanical input minus the losses, which is mechanical output. So in this case, then cancel out is 1 minus E mechanical loss divided by mechanical. Is that okay? At this point, because you see here that E mechanical out is E mechanical in minus losses. So E mechanical in minus losses there. So divided by mechanical in, so remaining 1 minus mechanical loss by mechanical in. So that is the thing there. And then the pump efficiency and turbine efficiency can be calculated. Neta pump is equal to mechanical power increase of the fluid by mechanical power input. So it can be written like this: the E mechanical fluid divided by mechanical the shaft work, because the pump shaft work of the pump, which is equal to the shaft work of the motors multiplied by the efficiency of the motor, which is equal to shaft work of the pump. So in this case, we can find that the mechanical power increase of the fluid, which is delta E mechanical fluid by mechanical energy absorbed by the shaft of the pump, which is W pump divided by that means the pump delivered the energy to the flowing fluid if it is W pump U divided by W pump shaft work. So in this case, we can write down delta E mechanical fluid is equal to delta is equal to E mechanical out minus E mechanical in. So with it, we can write down eta turbine. Turbine is mechanical power output by mechanical power decrease of the fluid. So you see the cursor there is equal to W shaft out by delta E mechanical fluid. So we can eta turbine, we can write down that W turbine, the amount of energy given to the turbine, and EW turbine extraction from the turbine is up numerator there, and denominator is the shaft work of the mechanical energy, or work mechanical energy supplied to the turbine is given down there. So with it, we can turbine efficiency can be evaluated there. So delta E mechanical is E mechanical in minus E mechanical out. So with it, see this problem, small problem with a fan, we can find out that here the fan there, so the fluid, if it is discharged at the atmosphere there, then the pump, fan power input is 50 watt here. You see the fan power input is 50 watt there. And then the mass flow rate of the fluid is this much kg per second there. So velocity here and velocity here, they're different because velocity approaching it is not the ram effect. There is no ram effect there. So we consider the velocity here is 0 there.
So in this case, the velocity at the discharge is 12.1 meter per second. So as they are on the same plane, so Z1 is equal to Z2. And P1 is equal to P atmosphere, that is the left side, and P2 is equal to P atmosphere, that is the right side of the fan there. So in this case, eta mechanical fan efficiency is equal to delta E mechanical fluid divided by W shaft. Is it okay? Delta E mechanical fluid divided by W shaft work. So mechanical fluid, this is kinetic energy, holding by the flowing fluid there, half mv squared that. So that is coming m into v2 squared by 2, and a shaft work is W shaft in there. That they say is 50 watt there. So that is in the denominator. So this is the efficiency 0.741 there. So we move on further there, that the eta motor, if the motor efficiency also given, not the 100% efficiency of the motor, is certain value of the motor efficiencies is indicated, then eta motor is equal to mechanical power output divided by electrical power input. That is the efficiency of the motor there. So W shaft out, that is the motor output there, mechanical energy out. And W electrical, that is the power or the energy consumed by the motor for running that shaft energy. So the generator, eta generator, can be electrical power by the mechanical powers. So that is efficiency. So if we say that the pump and motor efficiency both there, then if you consider, then need to multiply the pump efficiency multiplied by the motor efficiency, that is giving us the overall efficiency of the motor and pump together, or you can say that eta pump motor can be represented by delta E mechanical fluid by W electrical. Pump motor overall efficiency. Is this all right? Because the pump outlet is coming to the fluid output of the pump, and the motor efficiency that is considered there, the motor power consumption, that is at the denominator there. So with it, we go to the turbine generator overall efficiency. We can go for the turbine and generator. So how the turbine and generator are linked to it? If it is the water turbine, then it operates at a low RPM there. If it is a steam turbine or gas turbine, it operates at a very high velocity there. So a very high RPM there. So in this case, the turbine, if we consider the turbine and generator efficiency, then we can say that eta turbine into eta generator here. You see here, eta turbine and eta generator, this one there also. So then it can be written that the generator produces electricity. How many watt it produces electricity divided by turbine shaft work. So this is equal to W electric output by delta E mechanical of the fluid there, because the fluid got the energy there, and then from the fluid energy there, what is that? And then the fluid energy, that is the water flowing through this water turbine, that is the fluid's energy. If we consider this, then that will give us W electric output by delta E mechanical fluid, that's giving us the overall efficiency of the generator and turbine there. So that is the information there we get, and then we can see that, okay, if the
if the turbine efficiency is 7.5 and pump generator efficiency is 9.7, then we get 0.73 there. So straight away we will, when we will solve problem, then straight away we'll use these two data and multiply, we'll get it there. So similarly, if we move on further there, then the mechanical energy when it is pumped, then is energy, mechanical system energy increases there. So in this case, E mechanical in minus E mechanical out, which is given us delta E mechanical system plus E mechanical losses there, which are physically they are the same there, because the mechanical in, if the losses are subtracted from there, losses will be negative there, and then which will be equal to the mechanical in minus E mechanical out. So with it, the unknown parameter can be evaluated. So in this case, we can write down that steady flow here, then what is the V1 here and V2 for the steady flow? Because the velocity at the this surface of the reservoir is and velocity at the surface of the discharge reservoir, in both the cases they are equal to 0. And the Z2, that point, the energy content is Z1 plus H, that is the energy content, and P1 will be higher than P2. Now P1 atmospheric pressure will be same in both the cases. So P1 is equal to P2 is equal to P atmosphere there. So in this case, if we calculate the E mechanical in, then we can write down this is equal to mechanical out plus the losses there, which is equal to the W pump, that is the pump work, then is the MZ into Z1 there, that is the MZ into Z1 indicates the potential energy there, which is indicating us MZZ2 plus E mechanical losses, which is virtually E. There's the W work is MGH plus the E mechanical losses there. So with it, we go to solve this problem here. So here you read the problem. This is the performance of a hydraulic turbine generator. Nowadays, people use the conservation of energy. So in hydroelectric power plant, people can pump the during the lean time, that can pump the fluid to a wherever the electricity is available at a low price, then pump to the upper reservoir there, and at the time of when it is the load increases, then that stored energy can be used for energy recovery. So this way, some sort of benefit can be obtained from this the energy storage principle. So with it, we come to solve one problem there. You read this problem, performance of a hydraulic turbine generator. So what do we find here? That is a leg on the left side of the turbine there, and a head is coming from the head of the leg, water head layer of the leg. And the outlet, the discharge side, is at a low head there. Discharge side is this one, discharge side. Sorry, I don't know where is the pointer here. So you see, this side is 0.2, and this side is 0.1. No, okay. The voice can increase. The voice should be okay. And now here, performance of hydraulic turbine generators. This data, they say that the elevation difference between the free surface upstream and downstream of the dam is 50 meter there. See the head difference, the 50 meter. So H into rho into G, that is the amount of pressure there available at this point. There, it can see that much pressure and energy flowing through this. So, and then this water is to be supplied at a rate of 5,000 kg per second, because in equation, mass flow is one of the factor there. So that is why this flow is more there, more energy is extracted in the turbine. If the electrical power generated is measured to be 1862 kilowatt and the generated efficiency is 95%, determine A, the overall efficiency of the turbine generated. So you see, overall efficiency of the turbine dash generator. What is the meaning of this? The meaning of it is that the efficiency of turbine multiplied by the efficiency of the generator there. Then the second part, need to calculate the mechanical efficiency of the turbine and see the shaft power supplied by the turbine to the generators. So in this case, if we have to go for the assumption the density of water is 1,000 kg per meter cube there. Normally it is vary within that range there. Maybe 0.998 or 997.9 if the too much cold there, then it's coming 1,000, something like this. So if we do the analysis there, then we can write it down that E mechanical in minus E mechanical out, which is equal to P in minus P out divided by rho there. This is nothing but our previous equation we use here, plus the kinetic energy, difference in kinetic energy there, V2 square minus V1 square, or V in minus V out squared by 2, plus Z into Z in minus Z out there. This is basically the potential energy difference. So with it, we can see here is no velocity, so this part is 0 there, and there is no pressure difference here and there because they are the same pressure atmosphere. This part also 0. Then Z into Z in minus Z out, which is equal to H. So then we get G into H there. So with G into H, we can get the mechanical, the energy available in the shaft of the turbine there. And that is equal to 9.81 into this H is 50 there, then use the conversion, then this with it we can get 0.491 kilojoule per kg there. So we move on further there, then delta E mechanical fluid, which is equal to M into E mechanical in minus E mechanical out there. So mechanical in minus mechanical out for unit is that much, 0.491. So for the mass 5,000 kg per second, we multiply it and get this much kilowatt. And in overall, that is the turbine and generator efficiency, if you consider there,
then generator output is electrical, and turbine input is the fluid head there. So if the fluid head is calculated this many kilowatt. So then this divided by this wheel, where we get this? Because the data is already given there, 1862 kilowatt power generated. So then we calculated this, and then the ratio giving us the overall efficiency there. Once we know the overall efficiency, if you know the turbine efficiency, generator efficiency can be calculated. So that is the turbine generated, eta turbine, eta generator from there, or the turbine efficiency. Generator efficiency is given here, you see 95%. So the turbine efficiency can be calculated, which is something like this. Shaft power output is determined from the definition of mechanical efficiency. So W shaft out is equal to eta turbine into E mechanical fluid, because 2455, this is the fluid containing this energy. So multiply by turbine efficiency, then the shaft will get this energy in the shaft, the rotating speed of the shaft. So that can be evaluated from this equation and find out this stuff there. Then another problem is solved there. Conservation of energy for an oscillating steel ball. So here you consider a steel ball is here. So you dropped it. You imagine that there is no friction loss and no heat generation, nothing. So then it will drop down from here and then go back to exactly at the same opposite side of this, because no losses there. So in this case, we can see that energy in minus energy out, net energy transfer. If heat is generated there and work is done there and the mass flow is varied, then we get the E in minus E out will be equal to delta E system there, will be equal to this. So with this, we go further there. There's W friction will be equal to kinetic energy plus potential energy minus kinetic energy plus potential energy at the second stage there. So the first step, if we consider the point here, then kinetic energy and potential energy here minus the kinetic energy, potential energy there, that will give us the W friction, how much. So with it, if we take the friction on right side of it, then we can write down V1 squared by 2 plus ZZ1 is equal to V2 squared by 2 plus ZZ2 plus the friction there. And for the idealized case of friction motion, the last friction reduces to like this. That is V1 squared by 2 ZZ1 is equal to V2 squared by 2 ZZ2, or V2 squared by, or V squared by 2 plus ZZ is equal to, as they are equal, then V squared as they are all equal, then V squared by 2 is equal plus ZZ is equal to constant there. So if it is that, and that constant is equal to how much? Because this is equal to the energy of this head multiplied by the G there. H rho G there, if it is a fluid, and H into G if it is solid there. So we get the C constant is equal to H into G there, where the value of the constant is C is equal to HG. This is when the friction effects are negligible and the sum of the kinetic and potential energy of the balls remains constant there. So with it, we move on further there. That is the Bernoulli's equation. So the Bernoulli's equation actually is the valid for these the
incompressible flow there, and consider that it is not valid in the wake region, or you see the wake region is here, the wake region here. And then the separation and reattachment region is this. So after all this region, this is Bernoulli's equation not valid. Rather, it's a valid outside the boundary layers. It's a valid here. And you see the streams are moving, flow streams are moving on here outside the affected region. Bernoulli equation not valid here, rather is valid here in this case. So we can say that the Bernoulli's equation is really an approximate equation that is valid only in invasive region of flow, where net viscous forces are negligibly small compared to inertia, gravitation, or pressure forces, such as regions occur outside the boundary and winds. In this case, we can write down for the Bernoulli's equation something like this, that streamwise acceleration, we can say AS is equal to, if it is the curvilinear, then streamwise there, then the acceleration can be V is equal to R into acceleration n there. So in this case, an can be said that V is squared by R there can be written. So it can also be written like that. Considering the straight path there, then R is becoming infinity. So this part will equal to 0, then it's coming n is equal to 0. So in this case, we can write down the Bernoulli's equation results from a force balance along a streamline. Can be write down dV is equal to delta V by delta S into ds plus delta V by delta T into dt there. So it can be written as delta V by rearranging this equation. It can be written d delta V dV by dt there is equal to del V by del S into ds by dt, and this is called del V by delta T. So now again, del V by delta T is equal to, because here the velocity remaining constant along the stream there, so the Bernoulli's equation, it can write down delta V by delta T is equal to 0. And V is equal to V into stream flow there. That is the horizontal stream, Vs. So in this case, we can write down As is equal to acceleration is equal to dV by dt there, and dV by dt from the previous expression. If this part is 0, see my cursor, this part is 0, so remaining this part there, this with it ds by dt is equal to V. So we say V d, so it can be acceleration is equal to V into dV by ds, or V is equal to ds by V is equal to what is the value of V, that is the velocity displacement by time. So from there, V is equal to ds by dt. So we can say that during steady flow, a fluid may not accelerate in time at a fixed point, but it may accelerate in space. So there, we're not considering this, we're considering the fixed flow in this case. So next, we move on further there, the deviation of the Bernoulli's equation there. Derivation, if we go for the derivation, then we can write down that the force or the total work done steady flow along a streamline, consider the streamline there, then we can say that Fs is equal to mass into acceleration. By definition, force is
mass into acceleration. So if we do the summation of forces on the object here along the streamline of fluid stream here on this rate, that package of fluid there, then it can be written Fs is equal to m into As. And with it, we can write down there the difference between these two there, P into dA minus P plus delta P into dA there. And is coming from the load, that weight, that component, so is minus then perpendicular to the surface. Need to consider that component here because perpendicular to the flow direction is considered the flow and the energy. So in this case, we consider the W into that is assigned there. So that is the perpendicular. So it's coming signed by hypotenuse. So it's coming minus W into sine there, which is equal to mv into dv by ds. So with it, we can write down m is equal to their rho v, because where v is the volumetric flow and rho is the density. So in this case, rho into dA into ds can be written there, and this then finally it can be written that the W is equal to mg. It can be written then, which is equal to rho g into dA into ds there, because the dA is the surface area and ds is the length of it, is giving the volume of the fluid package. And from there, it can be said that multiplied by rho then is giving us the mass of flow of the fluid package there. So with it, we can write down sine theta. This from the previous equation, can write down sine theta is equal to dz by ds. That is from there. Finally, it can be written minus dpdA rho g dA ds dz by ds. And from there, rho dA into ds v dv by ds. So with it, rearranging this equation, dp is equal to rho g the minus dp minus rho g dz is equal to rho v dv. And here v into dv is equal to half into differential of v squared. Can be written like this because in that case it will come in the same thing that which is represented by v into dv. So with it, we rearranging the equation, then can get dp by rho plus half dv squared by g dz is equal to 0. Then integration of dp by p plus v squared by 2 plus zz is equal to constant there, because the half and this thing is taken to the right side. If integrated, then dv square integrated d is down there, remaining v squared by 2. And then plus z, that is the constant along a streamline there. So steady incompressible flow is valid for the Bernoulli's equation, which is giving us P by gamma plus V squared by 2 plus GZ. So if gamma is a remaining constant there, then integration of dP is giving us P. So it's giving P by rho plus V squared by 2 plus ZZ. That is the constant along the streamline here. So if 2 points on the streamline there, 2 points there, 1 and 2 there, then we can write down P1 by rho plus V1 squared by 2 plus ZZ1 is equal to P2 by rho plus V2 squared by 2 plus ZZ2. So with this understanding,
we can write down for steady flow along a streamline. General equation is Bernoulli's equation. General equation is integration dp by rho plus v squared by 2 plus z is equal to constant. And for the incompressible flow, rho is equal to constant there because it cannot be compressed. So as a constant value, and then it's coming p by rho plus v squared by 2 plus z is equal to constant. So we can say that the incompressible Bernoulli equation is derived assuming incompressible flow, and thus it should not be used for flows with significant compressibility effect, because have to be used with a Mach number 0.3 and around in that. Because if the Mach number is going higher and higher, then it's showing the compressibility effect there. So that should be realized in mind. So then with this, we can write down that this flow energy or the pressure head is P by rho plus this kinetic energy V squared by 2 plus the Z, that is potential energy, is always constant if we consider a streamline flow and horizontal stream there. And incompressible flow need to consider there. And this Bernoulli's equation can be viewed as the conservation of a mechanical energy principle, and this is equivalent to the general conservation of energy principle for systems that do not involve any conservation of mechanical energy and thermal energy to each other, and thus the mechanical energy and thermal energy are conserved. And there is no dissipation of mechanical energy during each flow there, because it's considered as this is a reversible process. If the dissipation there, then this doesn't remain constant. The energy content, because some energy will be for heating and that purpose will be lost. This is a very assumption of it. And the Bernoulli's equation is commonly used to have in practice, since a variety of practical fluid flow problems can be analyzed to a reasonable accuracy. Though it is not 100% correct, but it can give us some estimation which is fair enough for using it. And this Bernoulli's equation states that the sum of the kinetic potential and this pressure or flow energy of a fluid particle is constant along the streamline during steady flow there. So with this understanding, we move on further there, that if you do the force balance across streamlines there, then we have the force balance in the direction N over there. This criteria is for the compressible flow there that is in the vertical direction if we have a component. So this force balance in the direction N normal to the streamline yields the following relation applied across the streamline for steady incompressible flow. So the horizontal you consider is incompressible flow. And if we say that, okay, this is compressible flow, incompressible flow, and the vertical component of the streamline we consider, then it can be written like P by rho plus V R into dN airs, and plus Z across the streamline. So we can say that for flow along a straight line, if it is, as we said earlier, it is equal to R to infinity. And this equation reduces to P by rho plus ZZ is equal to constant, or P is equal to, we can say minus rho ZZ plus constant. We can say it like this. So rho gz going to this side and multiply by constant is remaining mathematically constant here. So with it, we can say that if in the vertical direction component we consider for the incompressible flow, then we can say that PA minus PB or PB minus PA, because the bottom there is the high pressure, will be equal to PD minus PC. And now for the RSTD compressible flow, we can write down dP by rho plus delta V by dt ds plus V squared by 2 plus Z is equal to constant for the RSTD compressible flow. So with it, we move on further there that static, dynamic, and stagnation pressures, if you consider, then what are the definitions of the static pressure, dynamic pressure, and stagnation pressure? Static pressure is considered pressure when no flow is being considered there. So if we consider the flow is flowing through the tube, then the static pressure is after the stagnation point, after the section, this measure the tube inner diameter and inner temperature of the fluid, that is the static pressure there. So P is the static pressure. It does not incorporate any dynamic effects, and it represents the actual thermodynamic pressure of the fluid. So the same as the pressure used in thermodynamics and property tables. And now, if we consider the kinetic, that is the energy of the pressure there, that is the dynamic pressure there, which is equal to rho V squared by 2. It's the dynamic pressure, and it represents the pressure arise when the fluid in motion is brought to suddenly stop there. That is the stagnation pressure there. And rho Z we can consider. So static pressure, we can consider that when this suddenly the flowing fluid is stopped due to some thrust over there, flow barrier or flow passage barrier there, that is indicated as the dynamic pressure, and it represents the pressure rise when the fluid in motion is about to stop isotropically there. And with it, we can say that rho ZZ is the hydrostatic pressure there, because it's coming through the potential energy. It's not pressure this is not the pressure, it is due to the height. That is, what is the height of the equipment being installed there. We consider that is there. So total pressure will be the sum of the static, dynamic, and hydrostatic pressure. And now the Bernoulli's equation states that the total pressure along the stream remaining constant. So the 0.1 and 0.2 there, then we can say that P1 plus V1 squared by 2 plus rho ZZ1 is equal to P2 plus rho V2 squared plus rho ZZ2. So with this, we move on further there, that just only another 3-4 slides, then we're finished. But today, Dr. Mishra will continue. Yes. So now, if you consider, this is the instrument called Pitot static tube there. So this Pitot static tube is used for measuring the velocity of the fluid there. And nowadays also anemometer is used by the people to measure it. But the old time, this is the anemometer, very sensitive there. So for the boiler and the flowing fluid there at high temperature, this is being used to Pitot static tube. So in this case, P stagnation pressure will be equal to pressure plus the kinetic, this energy. The pressure head, kinetic pressure head there. So rho V squared by 2 there. So this is the stagnation pressure here. And static pressure at a certain distance from there We made a hole in the instrument there and measured the pressure here, which is giving us the static pressure at the holes. So then the velocity can be evaluated like this. Power 2, you multiply by this, and that's divided by rho there. I'm going to calculate the velocity here. And what we find here that the static pressure is low than the stagnation pressure there. You see, this is due to the velocity of it is gone up. So this piezometer can be used there to measure the pressure there, and proportional to static pressure is giving P there, which is giving this hole there. And the stagnation pressure, which is this pressure plus this square by 2g. So with it, we use the pitted static tube to measure pressure there, and velocity is equal to represented by this equation. So now we come to, if we use this instrument, and if the instrument is fabricated like this flower over there, you see this, then it will show the height value of this that stagnation pressure. So if no such this flow there, then it will give us this data. And if it is moving on this way, then the separation will happen there. Then we get the drop down to this. So careless drilling of the static pressure tap may result in an erroneous reading of the static pressure head. Now we consider the stagnation pressure. This is the aerofoil here. Then the stagnation pressure in the aerofoil will get to here, and the stagnation static pressure will get to here. So that from this we can find out the difference between the static and stagnation. The straight lines produced by this this introduced upper stream of an airflow, since the flow is steady, the straight lines are the same as streamlines and path lines. The streamline is not there like it. Then we have still there are limitations of the Bernoulli's equation. I think we will finish with the limitations. Then hydraulic grade line, and this from there the potential rules. So these are the limitations on the use of the Bernoulli's equation. Number is that one is that it has to be in the steady flow, because we have, when it is being derived, then we have seen that it has to be the steady flow and should not be in the separation zone. It has to be outside the boundary layer, and then this Bernoulli's equation prevails there. And second thing is that friction losses or friction these losses will be neglected, because there is no frictional flow yet, so that it's a reversible process. Not the reality there, but it's a reversible process there. Then number three is no shaft work there. If some shaft work is there, then energy will be lost to there. Then we will have P1 and P2. When we will equate, this will not be equated unless we add the shaft work there. And in compressible flow, we consider there, in compressible flow, in this case, we consider the Mach number here. You see the cursor about 0.3 there. And no heat transfer. If the heat transfer there, then the energy will be lost there and process parameters will be changed. And flow along a streamline, strictly speaking, the Bernoulli's equation is applicable along the streamline. When a region of the flow is rotational and there is negligible small vorticity in the flow field, the Bernoulli's equation becomes applicable across the streamlines as well, but these will be negligible vorticity. So here the limitations, so you can see one there, you see these sudden expansion flow. This is the backward facing step. Similarly, like a forward facing step, in both the cases, Bernoulli's equation cannot be valid there. There are different equations for those. And a long narrow tube there, if it is the 1 and 2, there is the 2 different points, then it's not valid. So then go to the 1 and 2 there, you can see this valve there. So here is the pressure loss there. So you do the throttling process, then here also the pressure loss, and then we get the energy changes there. It's not valid. And then the fan, these 1 and is the pressure is here low and the pressure high there, and it has got the losses in it there. And because the say the pressure here and here remaining different, but when it is running, then it introduces energy there. So any input of energy will not be valid, the Bernoulli's equation. And if you're heating it up, there will not be valid. So in the wake region, it's not valid there. So it's in the outside the boundary layer is valid. So in this case, we can say that the streamlines case V1 by rho plus V1 squared by 2 plus Z by Z1 is equal to P2 by gamma 0.1 and 0.2 there, because these, you see the head there, this the elevation 1, and this is not the hydraulic head, this is the elevation. So this is the 1 and 2 there. Then we can equate the this Bernoulli's equation like this: P1 by rho plus the V1 squared by 2 is ZZ1 is P2 by rho plus the V2 squared by 2 plus Z2. So we did. We would like to come to the end of today's discussion. Now I'd like to go to you. If you have any question, please ask so that we can have 74. I think Ms. Klasi, he will finish and then he will go to refrigeration. Is any question you have? These Jeremy, Yok Feng, Wei Jian, Noor, yes, please. Please, Noor, you have any question?
Hello, doctor.
Noor, do you have any question?
Can you hear me?
Hello.
Can you hear me?
Yeah, I can hear you. No problem.
Let's say after this lecture, if we have any question, where do we? I mean, should we drop you an email
You
or
can
we
send
can ask
in
you
the
through
WhatsApp
WhatsApp?
also, and
Okay.
then can also, because if you don't have enough time to ask question, then after this any question you can ask now or later on, no problem, because we continuous education, we keep going on continuously.
All right. Also,
Is that
will
okay?
this lecture be recorded? And
Yeah,
where
the
can I
second
find the recorded lecture?
This somebody is anybody did the recording. If not, then I will upload all these reading material to the Spectrum, so you can get all this material in the Spectrum. Is it okay? Only the books cannot be uploaded, but chapter book.
I see that you are currently
Chapter.
recording. Hello, sorry.
This lecture is recorded, so later you can find in the chat box.
Yeah, correct. This recording. Yeah, I see this recording has started. I believe they have done the recording. And then you can also upload the recording in the with group, because we made a group, huh? Right? You hearing me? We made a group, huh? There, and then many of you joined there. I think Dr. Shu can also use the same group there, so that any information can be posted there. That will be much easier than going through the spectrum. Huh? Is it okay?
I think it's fine with me.
Yeah. So once again, that 20 marks for class test, 10 marks for group assignment, 20 marks submit individual assignment, and 50 marks final exam, 3 questions, each question containing a bit theoretical part and problem solving. This is our style. Huh? We'll go like this. Is it okay? Yak Feng, is it okay? Jeremy, is it okay? Wei Jiang Bei, Muhammad, Noor, Adi, Noor Adi, is it all right? Brian, is it okay?
Yeah.
Shakira? Okay, so next class exactly at the same time the next week, and Dr. Nashul will come into picture, and then he will tell you, because sometimes it's easier to give the link you before 5 minutes, because if they are late in taking the class, then it's better to give the link before the class starts. Earlier giving and then not coming into is a problem. Huh? So okay, see you in the next class.
Hello, doctor.
Yeah.
My request to be in the Microsoft in the Teams group is not accepted yet, so I couldn't chat or check the chat box.
Yeah, can.
Yeah, because I don't know. I've already requested. No, I've already requested to be in the group under the Microsoft team, but my request is not accepted yet. So, I mean, I need a favor to accept it.
Yeah, okay. We'll give you.
I also, Dr. Kazi, I also don't have the chat box as well.
Oh, okay.
Yeah, so you have to accept our request so we can get in the group.
Yeah, okay. Yeah.
Right. Thank you. Okay. Thank you, doctor.
We'll do it. No problem.
All right.
Thank you. Bye now.
Bye.